Okay, today we are going to see one of the very valuable electro-analytical technique for the determination of species concentration as well as the electrochemical reactions. Why we are seeing this is one of the tools that are used in the field cell research to find out the possibility of the reactions. We will come to it later on. This is a slight deviation. We wanted to do the polymer electrolyte membrane fuel cells, but before that this topic has come up, so we are doing this today. Now essentially what we are doing in all these things is some kind of a electron transfer reactions. Now I hope you are able to see the electron transfer reaction is the fluorine getting reduced to fluoride ions. The potential that you are developing is 2.87 volts, and lithium ion plus electron giving rise to lithium, which is not a feasible reaction, therefore the potential is minus 3.5. The reverse reaction is the feasible reaction, because the reverse reaction gives rise to lithium ion, which is a stable configuration. Here the fluorine is taking up to electrons to give rise to a stable fluoride ion configuration. So therefore the potential is positive, the potential is negative, or the free energy is negative here. The free energy in the lithium ion plus electron giving rise to lithium is free energy is positive, therefore this reaction is not thermodynamically spontaneous. So now in all these things, what we are measuring is the some kind of a voltammetric methods. Voltammetric methods means you are applying an voltage and measuring the current. Okay, in all these things you have to use a 3 electrode system. Maybe we will discuss this at a later stage, because the potential is applied between the working electrode and a reference electrode. The electrochemical process is taking place between the working electrode and the counter electrode. So therefore the application of the potential on the electrode is an absolute measure of with respect to the reference electrode. The electrochemical reaction that you are measuring, the current or whatever you are measuring, is between the working electrode and the counter electrode. That is why you are having a three electrode system. Okay, we will assume it that for the moment we know we have to do this in a 3 electrode system. Later on we will look at it little bit more carefully. There are various voltammetric techniques that are possible. uh, that is, how are we scanning the potential? Okay, the potential can be scanned in a number of ways. Here I have given some ramps. It can be linearly varied, or it can be cyclically varied, or it can be with a AC ripple we can do, or one can use a differential pulse, or one can also do a pulse. So the response in the current voltage curve. Okay, here even though it is given as polarigram, it is current voltage curve. Voltage is in the x-axis, current is in the y-axis. So you can see how the current is varying when we use various kinds of ramps. Whether when we use the continuous variation of the potential with respect to time, a linear fashion, the current increases and reaches a saturation value. Whereas when I ramp it in a triangular fashion, it gives rise to a loop, a closed loop, which is called the cyclic voltammetry normally. When I apply as the AC pulse, at the AC pulse time, I will get a current signal. Otherwise, the signal will be uniform only at the AC ripple situation. So the same thing holds good for a differential pulse. The same thing, similar thing is holding good for the pulse. So therefore, generally what we are talking about is the linear variation of the potential with respect to time. Now in all these measurements, what we are doing is we are measuring this current under the very high concentration of the supporting electrolyte. Here I have given some typical measurement. The concentration of the supporting electrolyte is 0 or 1 molar. So you can see when it is 0, the total current that is measured, which may be due to the electrochemical reaction that is taking place with respect to the substrate that is present. This can be due to two reasons. One is because of the migration of the ions. Second one is the diffusion of the ions. What we essentially want to do is to measure the diffusion of the diffusion current, so that we will be able to determine the concentration of the species. When the migration is taking place, the concentration will be varying or decreasing enormously. So therefore, in all these measurements, we have to use a supporting electrolyte, which is going to be very high concentration of the order of 1 molar concentration. And the nature of the supporting electrolyte must be having the same mobility for the cation and anion, potassium nitrate, ammonium nitrate, like that, okay, or quaternary ammonium salt, like that. Okay, so the migration current, if I were to subtract, migration current is of the order of 9.2 microamperes, and the diffusion current is 8.45. At one molar concentration, I'm only measuring the diffusion current. I'm eliminating the migration current. So therefore, in all these electrochemical measurements, it is necessary that we have to use a supporting electrolyte. Potential is continuously changed as a linear function of time. So here there is a trick. Potential versus current is a thermodynamic parameter. Potential itself is a function of time. Now it is a kinetic parameter. So you see, in the one and the same cyclic voltagram, I can get the thermodynamic parameter as well as I can get the kinetic parameter. In the cyclic voltagram, in which the direction of the potential is reversed at the end of the first scan, thus the waveform is usually in the form of the isosceles triangle. Okay, potential increases like this, decreases here, then it goes in the other direction, increases in the other direction, and then decreases. So this is the one cycle of the potential variation of the working electrode with respect to potential. Okay, advantage is that the product of the electron transfer reaction that occurred in the forward scan can be easily probed again in the reverse scan. If I have oxidized something in the forward scan, it should get reduced in the reverse scan, if it is a completely reversible reaction. If it is not completely reversible reaction, the forward scan current and the backward scan current, they cannot be equal. One must be higher than the other. Okay, this anodic current will be around 1.2 to 1.3 times that of the cathodic current. Powerful tool for the determination of formal redox potential. I will come to it in a minute. Why formal redox potential? It is better to have the redox potential. Okay, thermodynamic reverse redox potential. But it is since we are using the concentration term, so we just a minute. Wait. So this is a powerful tool for the study of the reversible reactions. It can also be used for study of the irreversible reactions. Okay. Now, because in the whatever has got oxidized in the forward scan can get reduced in the reverse scan. So therefore, the current in the anodic peak IPA must be equal to IPC. Now the potential difference between these two, okay, the IPA and IPC will be a function of 0.59 millivolts. 59 by n. N is the number of electron transferred. If it is 59 millivolts, then it is one electron transfer. If it is 59 by n, then it is n electron transfer. That is the first problem. Second problem is, if I were to take the width of the peak at the uh, half height of half the HW FW full width at half maximum, okay, full width at half maximum of the peak, then it will have a definite value for a reversible process. We will consider this later on when we are going to do little bit more of the deeper in electrochemistry. Why it should be like that, okay? It should be 59 by 2 or by 59 by 2 n. Okay, we will see later. There are two conventions that are followed in the literature. Okay, so therefore those of you we are studying this in the or looking at the papers published in this, one has to be aware of this. The iupaccalic convention is anodic peak followed by cathodic peak. Okay, anodic peak goes to the upper side or the first quadrant. Cathodic peak goes to the fourth quadrant. But this is exactly opposite to the American convention. American convention is the cathodic peak is gone first and then anodic peak is the fourth quadrant. Therefore, in the literature, if you see, this difference will be existing always. So we have to be careful in understanding whether we are talking about the anodic scan or cathodic scan. Okay, there are few other aspects that we have to worry about it. Just like any solid surface, here is an electrode that is being used. Therefore, heterogeneity is a common feature of all electrochemical analytical techniques. Why electro-analytical technique is? Electro-analytical technique is a very selective technique. It will not be interfered by other ions, other species that are present. Whereas if I go to spectral photometry, or if I go to chemical analysis, quantitative chemical analysis and all those things, if two species are capable of getting reduced, both will get reduced. Whereas here, the one of the species will get reduced at a particular potential, the other species will get reduced at another potential. Therefore, it can be more specific. Okay, essentially what we are doing it is we are looking at the electron transfer that is taking place between an ionic conductor and a electron conductor. Electron conductor is the electrode metal. Ion conductor is the solution where the ions are present. So wherever the electron transfer is taking place with the electrode, that electrode is called the working electrode. Whereas the counter electrode is called the electrochemical reaction taking place is called the second counter electrode. A second electrode, which is a constant potential, is called the reference electrode. So reference electrode versus the working electrode gives me potential. Current working electrode versus the counter electrode gives me the electrochemical reaction that is taking place. Amount of this substance heat required here is very small. It can be 1 micromolar or even less than that. Whereas the supporting electrolyte has to be 1 molar. Okay. So therefore, since we are interested in identifying analysis, okay, identifying the chemical species that is present, a very small amount is enough for this technique. So now a typical voltammogram is shown here in the left hand side, and the right hand side we are talking about the reduction of the ferrocene at various scan speeds. Okay, scan rate. That is, how am I varying the potential as a function of time? That is what is shown here. And at the bottom, I have shown how the current is varying with respect to square root of the scan rate. So now the points that we understand here are: one, you see the scan rate is changing from 50 millivolts to nearly 500 millivolts per second. Now the peak potential is changing its position. I hope you are able to. Simultaneously, the current also is increasing, and the current is linearly increasing. If it is not linearly increasing, then it means that the process is not a reversible process. If it is linearly increasing, maybe it is a reversible process. But at very high current densities, this linear variation may not be holding good. So different ways of doing voltammetry is I can do a potential sweep, potential step function I can do, or linear sweep, continuously I can vary. When I do a linear sweep, then it is called cyclic voltammetry. So cyclic voltammetry is a technique used technique for studying electrode process, particularly by non-electrochemists. Apply continuous cyclic potential to the working electrode. The effects that we are measuring is Faraday's reaction, that is oxidation reduction of electroactive substance, adsorption desorption due to the potential, capacitive current, that is double layer charging. All those things are we are measuring. So deviation from the steady state, that is dc by dt, is not equal to 0. Therefore we can monitor the concentration. So therefore if the anodic peak current and the cathodic peak current are equal, we have already talked about it, then it's a reverse couple. If they are not equal, then it is a irreversible process. Now we are talking about the E0, the standard reduction potential, is the EPA plus EPC divided by 2 is the standard reduction potential. Okay, here I have shown for a reversal couple, the separation of the peaks for a reversal couple, we have already talked about it, is 0.59 by n. Okay, for a single electron transfer, it should be the separation between this peak and the anodic peak and the cathodic peak must be 59 millivolts. Now all these things are holding good only when I have the transfer coefficient as 0.5. Normally we are assuming that the transfer coefficient is 0.5. But when alpha deviates from 0.5, the voltogram becomes asymmetric. Cathodic peak is sharper as expected from the Butler-Varma equation. We will see later on what is Butler-Varma. Already we have talked about it, that the current should be linearly varying with respect to the square root of the scan rate for a reversible process. So in summary, what we are talking about it, what is the peak current? How does it depend upon? Okay, it depends upon diffusion to the diffusion coefficient to the power of half, n to the power of half, area of the electrode, and then the number of electrons transferred. All those things, all of them are fixed quantity. We can put it into a constant. IP is still proportional to the bulk concentration, but will be lower in height depending upon the value of alpha, if it is a irreversible process. Assuming alpha is equal to 0.5, the ratio of the reversible to irreversible current peaks is 1.27. If that peak heights are anodic peak and cathodic peak is not equal to 1, automatically it implies that it is having a irreversible process or quasi-irreversible process. Okay, you can even get the kinetic constants. Shape of the cyclic voltammeter is a function of the ratio of these parameters. As the ratio increases, the process approaches to the reversal process. So here I have given only one or two examples only we are going to take today. The one of the example is many other possibilities. Many possibilities. You should not go with the idea that I can only study the electrochemical reactions. Here I have shown a reaction ECE, electrochemical reaction followed by chemical reaction followed by electrochemical reaction. So now you can see oxidation process plus electron giving rise to reduction. The reduction process in a chemical reaction converts into R goes to S. That S undergoes another reduction reaction. Okay, so this is a electrochemical reaction followed by a chemical reaction followed by an electrochemical reaction. So you can see the corresponding cyclic voltammeter. You see what you are seeing here is two anodic reduction peaks, two anodic peaks and one cathodic peak. Okay, so the two oxidations that are possible there, it's shown there, but okay, in the cathodic region it gives you only one. We can also have a process where I have only one electrochemical reaction and another catalytic reaction. Now you can see when I do that, I'm sure you are able to see the peak. The electrochemical process is gives us a signal very well, but the catalytic process is a very small signal. Okay, oxide species regenerated and is re-reduced, whereas S is more difficult to reduce than oxygen here. That is why it is having a smaller peak compared to the first electrochemical reaction. So this type of complex reactions where electrochemical reaction followed by chemical reaction or chemical reaction followed by electrochemical reactions. This type of very complicated reactions can be studied. What we are doing it, I have already told you, is that we are going in a potential sweep to the highest value and to the lowest value, and we are repeating this. That is what we are doing. So now the situation is current versus potential versus time. So I have a three-dimensional way of looking at the data. Okay, response. So therefore, that is one way of understanding. Another way of understanding is potential versus current is a thermodynamic function. Current time versus current is a kinetic version. So one can study both of them simultaneously here. Okay, current versus time, potential versus time. Okay, so in principle, what we can do at the first level analysis is I can take any electrochemically active substance and identify that what it is, what is its concentration, how much it is present, and all those things. Okay, start analysis with this CV. If I have an unknown system, the best thing would be to put a CV, find the reduction potential, and match it with the reduction potential of the system. Now, if in addition to the electrochemical reduction, other processes are taking place, then we can use the cyclic voltammeter peaks and analyze them. So we can even analyze and get idea about the intermediate species. For example, I have nitrobenzene; it gives hydroxylamine, and then goes to amide. All these things will be manifested there. So all these intermediate species also will be there. So it gives me not only a qualitative information about the process that is taking place, it can give me a certain amount of information about the process that is taking place. There are certain very specific diagnostic criteria. For example, one of them is the peak separation must be 59 millivolts or 59.5 n millivolts. Okay, that is one thing. If it is a, let us assume 59 by 2 is 29 millivolts, then you can say 2 electrons are involved. Then I have told you the FWHM has to be a function of the 59 by n, like that. Many other things are possible. Okay, we have very lot of information that is available, but one has to put in effort to extract out this information from this. So the measured current is due to the Faraday current, that is the electrochemical reaction that is taking place, and also the capacity current. The Faraday current is due to the electrochemical reaction. Capacity current is the charging of the double layer. So the total current that we measure is the IF plus IC. Okay. So IC, the double layer capacitor current is the capacitor into dE by the variation of the potential with respect to time. So we can do that. So therefore, what we need for doing all these things is we can apply the Nernst equation, get the equilibrium values, whether it is a reversal process, whether it is all those things. We can apply Butler-Lambda equation, we will be able to get the kinetics of the process. If we use the diffusion equation, then the mass transfer process will be there. Double layer charging and capacitance, if I measure, then I will know whether its absorption is important or not. So you see, only one cyclic voltammeter measure, but how it is coupled to many manifestations of the phenomenon: kinetics, thermodynamics, diffusion, double layer capacitance, all those things. Okay, so in the cyclic voltagram, normally what we are doing is sweep rate, so many millivolts per second is what we are doing. Okay, and we are measuring the maximum potential, IPA or IPC is what we are doing. So now quickly looking at it, okay, we will take another 5 minutes and to complete it. Sweep rates, three ranges of operation, very slow sweep rate. Okay, 0.1 to 2 millivolts per second. Then quasi steady state conditions, sweep rate and reversal, no effect on current versus potential. Corrosion, passivation, fuel cell reactions can be studied with them. Oxidation reduction of the species in the bulk, the sweep rates can be 0.01 volt, 0.01 volt. Okay, you should not think 0.01 millivolt. Okay, the first one is 0.1 millivolt to 2 millivolts. This is electrochemical oxidation reduction speed is 0.01 volt to 200 volts per second. So the time scales that we are measuring is of the order of 10 seconds for the mass transport. It gives rise to double layer charging, uncompensated solution resistance. Oxidation reduction species on the surface is once again the same potential scan 0.01 volt to 100 volts. Okay, here I have shown it. Here I have shown it how the current is there. Okay, current is varying with respect to, I hope you are able to see, in the x-axis we are plotting the log V, y-axis is the current. What we are doing is optimum range of concentration of the sweep rate. So if I will go on changing the concentration of the species in the solution 0.01 millimolar to 100 millimolar, how the current will vary with respect to potential is shown here. Okay. So this is a typical voltammegram that is available to us, which is studying the reduction and oxidation of iron 2 plus to iron 3 plus to iron 3 plus to iron 2 plus. So anodically I oxidize Fe2 plus to Fe3 plus. Cathodically I reduce the Fe3 plus to Fe2 plus. Okay. So this anodic is the first quadrant and the cathodic is the third quadrant. I hope you are able to see. This is the first quadrant is oxidation, third quadrant is the reduction. Now, in all these things, we have already told that there is an interplay of diffusion, mass transport, and charge. Okay. Now, simple phenomenologically, what we are talking about it, we are getting the activation control current and diffusion control current. So, therefore, the total current is going to be the inverse of the current is 1 over J, 1 over I, whichever symbol you use, is the activation control current and the diffusion control current. But initially activation control current will be very small compared to the diffusion current. So the J will be very much equal to activation control in the initial. But J increases with the potential, therefore diffusion current overcomes the activation current. E grows, therefore A activity increases, J diffusion decreases, therefore, and finally what happens is J activation control or the current for the activation control becomes equal to J diffusion control, that is the maximum. So therefore further progress depends upon when I get only the activation control is overcome, the process is controlled by the diffusion. So this is what is happening at the electrode. We will stop with this slide. We have a metal electrode, we have a solution, oxidized species gets reduced species get oxidized. So the extent of reduction or oxidation taking place is given by the fixed second law of the way. So naturally they will have any boundary conditions. Boundary conditions are shown here. So therefore the mass transport is what is the controlling this. So we will take it up in the next class, next presentation, the consequences of all these things in the PowerPoint projections of all these things are already with you. When you have time, you can look at it. We can see, for example, here is a multi-electron transfer of a paranitrophenol going rise to aminophenol up to that time, or so therefore we will have a multiple peaks which will denote the multiple process. In the same way, we can also look at the titanium 4 plus going to titanium 3 plus getting oxidized to titanium 4 plus, titanium 2 plus getting oxidized to titanium 3 plus. All these two situations, TiO can undergo oxidation to Ti3 plus, TiO where titanium is in 2 plus. Ti2 plus goes to Ti3 plus, the Ti3 plus goes to Ti4 plus, so we'll be able to look at the two reduction steps completely, and I hope you are able to see the difference between them is nearly 59 volts, 60 volts, so that is 60 millivolts. So therefore that itself shows that this both of them are reversal process. So with all these things we will see later on next time what are the possibilities of using this in the fuel cell reactions. So if you have any questions, we will answer them now.